Hi guys, I want to have two separate videos for you tonight. So one video is going to go over how we can calculate a half-life reaction, and then the other video is going to start talking about ionic compounds or ionic bonding. So for the half-lives, we started, or at least we tried to finish today, all the different types of decay reactions. So there's alpha, beta, gamma, there's a positron, and then there's also electron capture. Now what I care that you are able to write in terms of a decay reaction are alpha, beta, gamma, and positron. And then I just want you to understand conceptually what happens in an electron capture reaction. Now, on the slide on your nuclear chemistry notes that goes over half-lives, and it says on there that it's a first-order reaction. First-order reaction simply means that one sample of concentration will be affected. So, for example, in your M&M half-life lab that you did, there was a sample of M&Ms, and the amount of M&Ms changed after every single half-life. So that's a first-order reaction because there's only one sample that's changing. A second-order reaction would be where you have two different samples and both of them are changing. A zero-order reaction would mean that the sample isn't changing at all. So that couldn't be a half-life example because you know that for a half-life you have to have something or a concentration or amount of sample that's changing. So half-lives are first-order reactions, which just means that one specific concentration or one amount of something will be changing, which in your case, what we did was the M&M lab, and those M&Ms, the amount of M&Ms that you had after each trial changed. So it's just like that. Now for half-lives, there's a calculation that we can use to figure out how much sample will be remaining. We could determine the time that it's going to take for a sample to go from the original amount to a specified amount. We can calculate a rate constant. So I want us to look at that equation, and then we're going to practice doing a few of them. So if you look on the Promethean board, and also on your slides, this is the reaction that we have right here to calculate half-lives. So Ln, which is means the natural log. No? Okay. Natural log is a button that you can find on your calculator, which is exactly what we will be using. So give me 1 second, I'll show you what that button looks like. Let's see your calculator. Thank you. So on your calculator, you have a button that says Ln. That's the button that we're going to be using, and that's called the natural log. With that, you will be taking the natural log. This is NT over NO. NT simply means the amount of the material that is remaining after a half-life. Pretty simple. So you have some half-lives that go on, and you have, maybe you started with 100 grams, and maybe there's only 25 grams left. So the 25 grams would be NT, which is the amount remaining after you go through some half-lives. NO represents the original amount. So maybe you started off, like we said, with 100 grams. That's what I would say for NO, because that's what I originally started out with. So that's the original amount. If I look back at my equation, I have the natural log of NT over NO. So what I have right now, the amount of material I have over the amount of material that I started with, that's going to equal a negative K. K is a rate constant. So K just stands for rate constant. So really, what I want you to understand for rate constant is that it's the speed, or it's the rate at which an element or a compound can decay. So it's how fast really this compound is going to decay. Every element or every material or compound has its own rate constant. And most often, either I will give you that or you're going to have to solve for that, okay? So K just means a rate constant. And it's really just trying to determine how fast a specific element or compound is going to decay. Now T, up here, which is right next to your rate constant, just stands for time. So if we go back to this equation, I have the natural log of the amount that remains over the original amount, and that's going to equal a negative rate constant times time. And so this would be a really good way that we could find, or this equation is how we typically find the rate constant, K. There's another reaction, or another equation that we need to look at, and this is what we find for our half-life. So if we wanted to solve for a half-life of an element, we're going to use this equation. T half just means half-life. So T half does not stand for time necessarily, it stands for half-life. So don't get this T half and this just regular T by itself for time confused. So T half stands for half-life. We have a number here which was calculated, and we're going to derive that when you take AP Physics, but we're not going to derive it in this class. And then K, which stands for your rate constant. Oh, so good. So we have half-life equals this number divided by the rate constant. So these are the two equations that we're going to use to calculate different things in terms of half-lives. So I have two practice problems that I've set up for you that I want us to walk through, so then that way we can have some examples of doing those. Tomorrow in class, I'm going to give you a little piece of paper that has 3 or 4 reactions on them that I want you to try to calculate the half-lives yourself for. So based on these two examples, the homework will be just like that for tomorrow. So let's do an example. Okay, here's my example. I want to know, what is the half-life of a 100-gram sample of N, which stands for nitrogen, so of nitrogen-16, that decays to 12.5 grams in 21.6 seconds. So let's read that again. What is the half-life of a 100-gram sample of nitrogen-16 that decays to 12.5 grams in 21.6 seconds? This is what I think you should do every time you see one of these types of problems. You need to immediately write down what you have. So then that way you know what variables you have, and then you can figure out what variables you need. So I know, first number here, what is the half-life of a 100-gram sample? I know that 100-gram sample will decay to 12.5 grams. So I had originally 100 grams. If that's my original amount, that's going to be my variable NO. So NO is going to equal 100 grams. I know that because it says I'm starting off with a 100-gram sample, and it's going to decay to 12.5 grams. And let's write our formula up here as well, so that way we can remember what it is. Okay, so here's my formula, and ultimately, that's one of the formulas, but there's another one. We want to figure out half-life. And I know that my half-life formula is T1 half equals 0.693 over K. So these are the two formulas that I have, and I just want to figure out all the information that we have from this problem first before we figure out what we need to do here. So in the problem, I need to try to find T half, or half-life. That's my goal. I want to try to figure this out. I have an original amount of sample, that's 100 grams. I know what the amount will be left after it has decayed. So I know that it went from 100 to 12.5. So 12.5 would be my remaining amount, which we symbolize as NT. So this would be 12.5. I also know that it decays from 100 grams to 12.5 grams in a certain amount of time. I know that it decays in 21.6 seconds. So I know that T is equal to 21.6. These are all the numbers that I was given, and I see here I have NO and I have NT. If I look up here at my first equation, I have NT, I have NO here. I have time, which is up here, and I need to find T half, but what am I missing? What don't I have, or what don't I know? And you should be saying K. I don't know what K is, but could I find K using this equation so then that way I can find my half-life. And you should be saying that you could. So I know NO, NT, and time. NT, NO, time. I could find K. And then once I have K, I can plug that in up here to find my half-life. So let's do that. Let's plug in everything so that way we'll just take it step by step. Which now I have to shift you. Okay, so we have the natural log of NT over NO. So we knew that our amount remaining NT was 12.5. So let's plug that in up top here, 12.5. And I know that the original amount was 100. So we're going to plug in 100 right here. Okay, that's going to equal, I'm trying to find this K value. I need to find the rate constant, so then that way I can find the half-life. So I'm just going to write a negative K, and then I know the time that it took to decay, because I told you that that was 21.6. So T equals 21.6 seconds. So that's what we're going to plug in here, right next to K, 21.6. Okay, so now on my calculator, what I would do, I would plug in 12.5 divided by 100, which gives you, which I can't think, I don't think you can see this. Ah, there we go. Gives you 0.125. So that means that I need to take the natural log of 0.125. I haven't done anything with that other side yet, so I'm just going to carry that down because I haven't done anything with that yet. I just want to get this to be simplified. So I took 12.5 divided by 100. I got 0.125. Now I'm going to say, I'm going to hit this LN button, and then I'm going to write 0.125, and then close that parenthesis, and equal. And I'm going to get this fantastic negative number that you can't see on your screen because it's too dark. There we go. But it's a negative 2.08. And that equals a negative K times 21.6. Can we find K now or get K by itself? You should be saying yes. How can I get K by itself? I can divide both sides by 21.6. So if I divide both sides by 21.6, I'm going to get 2.08 divided by 21.6. That gives me 0.096, and that's a negative. That equals a negative K. So really, K would just equal, because two negatives, they're both negative, so it would both be like they're positive. So it'd really be K equals 0.096. So now we have K. So now I could find my half-life, because I know up here, half-life equals 0.693 over K. Well, I just have that number, it's a constant, and I know what K is now, so I could find my half-life. So let's do that. Let's find our half-life. My half-life would be 0.693 over K. Well, we just solved for K. We know that K is equal to 0.096. So we're just going to plug in that value underneath here. Now, if we divide 0.693 divided by 0.096, we get 7.22. So T half equals 7.22. So that means that this went through roughly 7 half-lives. Okay? So you have solved your problem. It takes a lot of steps. It's pretty lengthy, and that's how some of these problems will be. So let's do another one just to make sure that we are okay on this. Guys, on your next one, we have thallium-208 has a half-life of 3.053 minutes. So I know that the half-life of thallium is 3.053 minutes. I want to know how long is it going to take for 120 grams to decay to 7.5 grams. So in this one, I have a half-life, I know